In this video, we'll explore causal discovery, a tool that helps us identify classes of plausible causal structures. This provides another opportunity for connecting sensitivity analyses to understand the robustness of our results. So far, we've relied on expert domain knowledge to construct causal graphs. But is it possible to take a more data-driven approach to constructing these graphs? That is, can we learn the structure of causal graphs from data? With some assumptions, it's possible, and this pursuit is called causal discovery. We'll be building on our deseparation toolset, but before we jump into that, let's fix some important ideas first. Recall that if we're able to deseparate x and y using a set of variables, say z equal to z1, z2, and z3, then x and y are conditionally independent given z. This is because we can block all paths carrying association between x and y. Deseparation idea is built up from dependence and independence relations in chains, force, and colliders, and these relations are the result of the causal Markov assumption. However, this isn't the direction of reasoning that we're interested in here. We're interested in the opposite direction because we're starting from the data, not the graph. From the data, we might observe that x and y are conditionally independent given z. When the data are jointly normally distributed, we can assess this with the linear regression model of x on y, or y on x with z1, z2, and z3 included. If we observe that x and y are conditionally independent given z in our data, then does that imply that x and y are deseparated given z? Actually, not necessarily. Let's take a look at a possible situation of concern. Suppose that in reality, x causes y, as shown by this causal graph. However, it has different effects in two groups. In group 1, increasing x by 1 increases y by 1 on average, and in group 2, the exact opposite happens. Increasing x by 1 decreases y by 1 on average. When we collect and analyze data in this situation, we very well might not be aware of these two groups, and we would observe no association between x and y because the effects in the two groups perfectly cancel out when analyzed as a whole. So we would have no reason to believe in an arrow between x and y, even though it truly should be there. Cases like this, where there's a perfect cancellation of effects, are called intransitive cases. Generally, these situations are rare, but they're an important thought experiment when thinking about how to go from data to causal structure. It is possible that the data mislead us as to the true structure of the graph. This is an example of a violation of what is known as the faithfulness assumption. The faithfulness assumption is as follows. If A, B, and C are three disjoint sets of variables in a DAG, the joint distribution of the data is faithful to the DAG if conditional independence between A and B, given C, implies that A and B are deseparated, given C. Essentially, when we make this assumption, we assume that the data are not misleading us as to the true causal structure. If we observe conditional independence in the data, we naturally expect the corresponding deseparation. Without making this assumption, we can't move forward with any meaningful structure learning because any conditional independence pattern in the data could mean anything about causal structure. We'll make this assumption of faithfulness when we perform causal discovery. The overall structure for causal discovery algorithms can be broken into two broad steps. The first step is to determine an overall graph skeleton. This entails knowing which variables are connected by an arrow, but not what direction the arrows point necessarily. The second step is to try and orient edges. Oftentimes, we'll only be able to orient some arrows. The ambiguity of the directions of other arrows generates a class of plausible causal structures. So let's build up the ideas for how we can implement these two steps. How might we determine the skeleton of a causal graph? Suppose we're in a situation where only variables A, B, C, and D matter. What conditional independence tests should we perform to check if A and B, for example, are directly connected by an arrow? Pause the video to think about your answer before continuing. It turns out that we'd have to check every possible set of conditioning variables that excludes A and B, including the empty set. Let's consider testing for conditional independence given the empty set. This is the same thing as testing for marginal independence. We could, for example, test this with a regression model of A on B or B on A. A non-significant p-value for the predictor coefficient would lead us to decide that there's no relationship between A and B. Thus, no arrow. Remember that we're doing this under the assumption of faithfulness. We're assuming, for example, that there's no perfect cancellation of effects going on to create this apparent lack of a relationship between A and B. But maybe instead, the empty set leads to the conclusion that A and B are marginally dependent. They are related. Does that mean that there's an arrow between A and B? Not necessarily. They could be dependent by being the end nodes of a fork or chain, but not necessarily by being directly connected. Suppose that I put C in the regression model of A on B. What if putting C in the model suggests a lack of conditional association between A and B? The data are indicating a conditional independence of A and B, given C. So under the assumption of faithfulness, C deseparates A and B, meaning that there is not a direct arrow between A and B. Well, perhaps conditioning on C doesn't make A and B independent either. That is, A and B are still dependent, conditional on C. Does that mean that there's a direct arrow between A and B? Not necessarily, because the structure might look like this ring. We also need to try to make A and B conditionally independent given D and given C and D. If none of these combinations of variables succeeds in making A and B conditionally independent, there must be an unblockable path between them, a direct edge between A and B. We don't know the direction of the arrow yet, but if no set of variables is able to block all paths between A and B, they must be directly connected. This series of conditional independence tests is how we make the skeleton of the causal graph. We try these conditional independence tests for every pair of variables. We've discussed the first step, building the graph skeleton. Now let's discuss how we could orient edges. Suppose we're looking at a connected pair of variables in the graph skeleton, x and y. We know that x and y are associated in the data, but this tells us nothing about the orientation of the arrows. It turns out when orienting edges, looking at two variables at a time won't get us anywhere. Looking at three variables at a time is more fruitful, though. If we have this x, y, z skeleton, we know that x and y are marginally associated and that y and z are marginally associated. So the arrows could fit any of these four patterns. We can distinguish between these four possibilities using a conditional independence test, like regression in certain settings. If x and z are conditionally independent given y, we know that any of the first three patterns are possible. If, however, we reject the null hypothesis of no relationship to conclude conditional dependence, we can definitively orient the edges as a collider. When we iteratively look at three variables at a time, conditional dependence relationships allow us to orient edges. All of these ideas put together forms the cornerstone causal discovery algorithm, the SGS algorithm, which is named for the creators' last names. We start with a complete undirected graph. All possible edges between variables are present. Then, for every pair of variables, x and y, we'll look at all sets z of other variables to see if we can make x and y conditionally independent. If any set z succeeds in making x and y conditionally independent, delete the edge between x and y. Steps 1 and 2 form the skeleton building phase of the algorithm. Steps 3 and 4 form the edge orienting phase. In step 3, we look at triples of variables to check conditional dependence relations to orient colliders. And orienting colliders can sometimes inform the orientation of other edges. This is often called inducing an orientation. So in step 4, like a jigsaw puzzle, we try to use the oriented colliders to orient other edges where possible. In the end, the output of causal discovery is a class, a collection of possible causal graphs. This class is formally called an equivalence class. For example, the three XYZ graphs here are indistinguishable from each other, and they form an equivalence class. We can succinctly summarize these combinations with what is called a graph pattern. A pattern is a visual representation of an equivalence class, and it's often the result that causal discovery algorithms will give. The undirected edges in the pattern reflect the ambiguity of the edge directions. Generally, software packages will give options to display the output as a pattern or show specific graph structures within the equivalence class. In summary, causal discovery is a procedure that helps us learn graph structure from data. It relies fundamentally on conditional independence tests to determine the graph skeleton and subsequently orient edges. While we focused on the data-driven aspect of the methodology, causal discovery algorithms can also incorporate prior knowledge about edge directions, and some variants can also reason about unmeasured variables. Causal discovery is a wonderful addition to our toolkit because it allows us to approach sensitivity analyses in another way. Equivalence classes of causal structures can indicate different conditional exchangeability conditions, which in turn can inform alternate analyses of our data.